When we put money into an account, we typically earn interest on the amount that's in the account. The rate at which interest is earned on invested money is proportional to the amount of money that's in the account. This proportionality constant is called the annual interest rate, R. I want to find the amount of money, S of t, in an account t years after a deposit of S naught is made. Please note here that we are assuming that the interest is compounded continuously, but in practice, interest is most typically compounded daily, monthly, or yearly. Now, since the rate of change of S of t is proportional to S of t itself, we have that ds dt is equal to R times S of t. That is, the rate at which the amount of money is growing is the interest rate times the amount of money in there, S of t. We can solve this differential equation by dividing by s and integrating to get that S of t is some constant k times e to the rt. And imposing our initial condition, S of 0 equals S naught, gives that S of t is S naught times e to the rt. So, the amount of money, S of t, in an account earning interest at a rate R after t years is given by the formula S of t equals S naught times e to the rt. Putting some numbers to our parameters, let's consider that we have an interest rate of 6% on money invested at age 22. By what multiple will your investment grow by the time you reach age 65? That is, how many times bigger will the amount of money you have at age 65 be compared to the amount you have at age 22? Well, the money you invest at age 22 will have t equals 43 years to grow until you reach age 65. At a 6% interest rate, your investment at age 65 will be worth S of 43, which is equal to S naught, the starting amount, times e to the 0.06 times 43, which comes to roughly 13.2 times S naught. Notice here that it doesn't matter what the starting amount is that you originally invest. You'll always have 13.2 times as much money as the original input. So we can conclude that your investment will be worth 13.2 times the original amount that you originally invested. As a quick example, if someone inherited, say, $100,000 at age 22, and they put it in an account that got 6% interest, until they retired at age 65, they would have roughly $1.3 million in that account. Unfortunately for most of us, we don't have $100,000 at age 22 to put in an account. Most people make consistent payments into their retirement account throughout their working years. So let's amend our model a little bit. We'll still let the amount of money t years after making an initial deposit of S naught be written as S of t. We just saw that if money is in an account earning an interest rate R, then S of t can be modeled by the initial value problem, ds dt is equal to R times S, where S of 0 is S naught. But suppose now that we make regular deposits totaling d dollars per year. How will this impact our differential equation? Well, here we'll have a constant amount in our rate of change of d. So now money is being added to the account in two ways, from interest and deposits, giving us the new differential equation, ds dt is equal to R times S plus d, where the initial amount S of 0 is still S naught. So we again have found a model that gives a linear differential equation, which we can solve to find S of t. Let's look at an example of that now. Suppose that you open a retirement account with 6% interest rate at age 22. You initially invest $1,000 and then deposit $6,000 per year until you retire at age 65. How much money will you have in the account when you retire? In terms of the variables we defined before, our question is, what is S of 43? Since we're given information on DSDT, we start by modeling DSDT using the interest rate of 6% and the yearly contribution amount of $6,000. That is, we have the differential equation DSDT equals 0.06S plus 6,000. And additionally, we have an initial deposit of $1,000, so S of 0 equals 1,000. And remember, the combination of a differential equation and initial condition make this an initial value problem. To find S of 43 now, we begin by solving the differential equation to find S of t. In standard form, our differential equation is ds dt minus 0.06s equals 6,000, which leads to the integrating factor mu equals e to the integral of negative 0.06 dt, which is e to the negative 0.06t, giving the general solution S of t is 1 over e to the negative 0.06t times the integral of e to the negative 0.06t times 6,000. We can factor 6,000 out of the integral and compute the integral of e to the negative 0.06t dt as 1 over negative 0.06 times e to the negative 0.06t plus some constant of integration c. And we can find c by using that S of 0 is 1,000, which we can write in terms of our formula as 6,000 times e to the 0.06 times 0 times 1 over negative 0.06 e to the negative 0.06 times 0 plus c. Since e to the 0 is just 1, this simplifies to 6,000 over negative 0.06 plus 6,000c, which is 6,000c minus 100,000. Adding 100,000 to both sides and dividing by 6,000 gives us that c is 101,000 over 6,000, or 101 over 6. And we find that S of t is 6,000 e to the negative 0.06t times 1 over negative 0.06 e to the negative 0.06t plus 101 over 6. And evaluating at 43 gives us that S of 43 is roughly 1,232,000. A little bit less than the person who inherited $100,000 and just put it in a bank account, making no more contributions.